Okay, so let's start. Today we will start so-called connectedness. Okay, this is basically the actually last subject before we do uh, applications. I think I'll spend like 2 weeks on this, and then in the last week we will do some more applications of this material to again analysis. All right, let's start with the definition of a connected subset. A subset E of a metric space xt uh, is called, well, we define disconnected subspace, disconnected if we can find open subsets A and B of X, of course, so that the following conditions are satisfied, so that first E will be in the union of these two subsets. Intersection of E with each of them will be non-empty, and the intersection of three of them will be empty. Okay. In other words, these two subsets should separate A into two pieces. Pieces of a piece of E which lies inside A and piece of E which lies inside B, and these two pieces should be disjoint, meaning that E intersection A intersection B should be uh, an empty set. Okay. Uh, Otherwise, I mean, if E is not disconnected, if E is not disconnected, we will say that E is connected. If X is, if we take E to be X, if E equals X and X is connected, then we say that xt is a connected space, connected metric space. Okay. If E is disconnected, so if I can write E, as the intersection, as the union of intersections of E with A and B, then we call this AB a separation of E. Okay. In case E is disconnected, then we say that then the pair of subsets AB as above is called a separation for E. Okay, because they separate E into two pieces. Okay, the key point is that A and B should be open sets. Okay, otherwise, of course, you can write any subset as the disjoint union of two subsets. But here the point is that this subset should be open. Okay. All right. Let's see another characterization of being disconnected or connected. Uh, Note that. So let me write as a remark. Uh, assume X is connected. Uh, okay. Or let me say first disconnected. And X is written like this for some open subsets. Open subsets with, since it is disconnected, we should have this. X intersection A should be non-empty. In other words, A should be non-empty and B should be non-empty. And the second condition is that X intersection A intersection B should be empty. Okay, so the above three conditions here, becomes this. X, well, actually we have three conditions. X is a union of these two. None of them is non-empty and their intersection is empty. In this case, note that in this case, both A and B are open. Therefore, A is equal to X minus B is both open and closed. Similarly, well, A is open because it is given to be open, and B is open, therefore X minus B is closed. Therefore, if X is disconnected, and if I can write X like this, satisfying these two conditions, then A should be both open and closed. Similarly, B should be is both open and closed. Okay. So if X is disconnected, then X should be written as the union of two subsets, and these two subsets should be disjoint, and actually they are both open and closed. So this means what? Hence, if X is connected, the only subset of X which is both open and closed should be closed subsets. The empty set and X itself. Okay, so if your space is connected, then the subsets of X, which are both open and closed, should be the empty set and X itself. If you have any other set which is both open and closed, and if it is not neither X or the empty set, then that subset uh, and and its complement would be a separation of X. Otherwise, otherwise, uh, in other words, uh, if A is an is a subset of X, which is both open and closed, so that A is neither empty set or X, then A comma B, which is X minus A, would be a separation. Separation. Separation for X. So this is one characterization of connected sets, namely the space should have no subset other than the empty set and itself, which is both open and closed. Okay, all right. All right. The first proposition we will consider is the following. Uh, the interval zero one is connected in R. The absolute value metric is connected. Okay, and basically this is the only non-trivial actually result in this section, in the part of this book related to connectedness. So let's see how we can prove this. So assume on the contrary that this subset E is disconnected, and AB is a separation. Okay, are open subsets so that these three conditions are satisfied. What are those? E should be a subset of this. Intersection of E with A would be non-empty. Intersection of E with B would be non-empty, and the intersection of three of them would be empty. All right. Well, how we will proceed? Okay, let's start with the endpoint 0. So let okay since E is a subset of this and E is the 0 one, since 0 is in E, which is in A union B, 0 is either A or in B. We may assume without loss of generality that 0 is an element of A. It can be an element of B also, but it is inside one of them, maybe both of them, but let's choose that, let's say that 0 is a subset, is an element of A. All right. Okay. Well, since A is open, since A is open, right, open subset, there is some R positive real number so that the so that we have so that 0 minus R, 0 plus R lies inside A. So I have this. 0 is here and R is here, and this part, okay, maybe the of course I have minus R part also, but I don't care about that part, so maybe I use a different color. Okay, so A should contain this. Okay, maybe more, but at least this part. And let's say 1 is here. Maybe A contains all of them, I don't know, but A at least contains this part. Maybe I write this. Okay. Yeah. Okay. Well, let C be this subset. Set of all positive numbers so that the interval 0A lies inside A. Okay. Well, certainly this set is not empty because it contains this R. Maybe let me say this is R0. Okay. Note that R0 is in C, so that C is not empty. And I also okay, ask this R to be less than R, less than 1. Okay. All right. Okay. Note that 1 is not in C because otherwise 0 1 would be A, and thus 0 1 my intersection B would be empty because the intersection of three subsets 0, 1, A and B is empty. So if 0, 1 lies completely inside A, then this had to be 0 because intersection of A with this one is 0, 1. So this would be empty, but that's a contradiction to the assumption that E intersection B is not empty. So hence 1 is not in B. Okay. So what is this C? C is the subset of real numbers, so that when you start from 0 and go along the axis, so that the interval 0 to R lies inside A, and we know that you cannot go up to 1 because 1 uh, cannot belong to this subset C. Okay, so in particular, C is bounded by 1 from above. So its supremum exists. Hence, uh, let's say, okay, x0 supremum of C exists. So what is this x0? X0 is this set. You start from 0, okay, and here is 1. X0 is somewhere here. It is not 1 because, well, actually it can be 1. I don't know. Yeah, but it is the supremum of this set. So it means what? Whenever you have something here, 0A, 0 R belongs to A. Okay, it is the supremum of all R's, so that 0 R lies inside A. Now 0, 1, x0 is clearly between 0 and 1. X0 is in 0, 1. Therefore, it is in this union. So we have two cases. What are those? Either x0 is in A or x0 is in B, right? Let's see what happens if x0 is in A. Well, if this is in A, then of course, since A is open, there is another interval. Let's say like this, delta interval, so that this interval lies also in A. But in this case, the interval 0 to, let's say, this R were already in A, but this part is already in A, so I can go a little bit further. So the interval 0 up to let's say x0 plus delta, maybe not delta but somewhere here, would be also in A. But that's a contradiction. Why is that? Because x0 was the supremum of such points, right? Nothing further, if you go beyond x0, an interval like this from 0 up to this point cannot lie inside A. Okay, so let me just write that down. If x0 is in A, then choosing delta positive so that x0 minus delta, x0 plus delta is in A, we see that the point x0 plus, well, let's say delta over 2. So, okay, yeah, let's say, okay. So let's say this is delta. So this much is delta, and this point is x0 plus delta over 2. So this point, x0 plus delta over 2. So the radius of this interval is delta, and I go up to this much. So we see that this point, or maybe I should say the interval 0 to x0 plus delta over 2 is in A, so that uh, you know, x0 plus delta over 2 would be in C, contradicting that x0 is the supremum of C, right? X0 was the supremum, but I found a real number which is larger than x0, and that's also in C. So hence x0 cannot belong to A. Okay, here I said x0 is either in A or B, and if x0 is in A, then we ended up with a contradiction. Hence x0 cannot be in A, so that x0 should be in B. But that will give another contradiction. Why is that? Let me draw you a picture again. Here is 0, here is 1, and here is x0. Well, x0 is in B will mean that B is also open. So there is an open subset. There is an open subset like this around x0. And we say radius again delta. And this thing should lie inside B because B is open. But then this point would be in where? This point would be inside A because 0 to x0 is in A, and it's also in B. So we see that x0 minus delta over 2 would be both in A and B, and also in the interval 0, 1, and that's a contradiction. Okay, let me write that down. Since B is also open, there is some delta positive, so that x0 minus delta, x0 plus delta is in B. In particular, x0 minus delta over 2. So it is this point. Okay. So x0 minus delta over 2. So delta is this distance, okay, the radius, and this point is x0 minus delta over 2. This point would be in B, and x0, this is less than x0, and I know that uh, everything between 0 and x0 lies inside C, right? C is so that you start from 0 up to R, it all lies in A. Therefore, and x0 is the border with that property. So this is also in x0 minus delta over 2 is in B, is in A, I am sorry. So that the intersection A, B, and 0, 1 is not empty. A contradiction, and this is a contradiction. Okay. So what did we see then? If we assume that uh, this set is disconnected, you ended up with contradiction, right? Here we had two cases, but each one uh, led us to a contradiction. Hence, the interval is connected. Okay. Do you have any questions so far? Yeah. Well, I don't know whether it is one. Why is that? Because you see, well, actually, it cannot be one. Why is that? Here it is. Okay. C, one cannot be in C. Why is that? Because if it is in C, then the interval 0, 1 would be in A, but then there would be no point of 0, 1 which would lie inside B, because the whole thing lies inside A. So no point of 0, 1 lies inside B in this case. Remember the definition of C. It is this set of all positive numbers so that 0, 1, so 0 R lies inside A. So if C lies inside, if 1 lies inside C, then the interval 0, 1 oh, I see your point. Okay, you are right. You are right. I should be more careful. Yeah, I see your point. I said 0, 1 is not here. Yeah. Okay. So I should have this, right? Okay. Yeah. But again, we would be okay. Suppose this is the case. All right. Uh, yeah. And I should say this. If this is the case, and since this shouldn't be empty, one should be in B. Yeah, but again, this would give us a contradiction. Why is that? If one is in B, since B is open, again, there is some uh, delta would be like this, so that this would lie inside B because B is open. Therefore, a point like this would be in B, but this point is strictly less than 1, therefore it lies inside A, and that would give us a contradiction. Yeah, right. I have to correct this part. Okay, now choosing delta so that 1 minus delta 1 plus delta in A would give us would okay, let me erase this part, would lead to a contradiction. Okay, in any case, okay, so this means what? Uh, okay, so hence one cannot be in C, and uh, C is bounded. Let again x0 be the supremum of C, and then we proceed. Uh, is it okay now? Okay. But thank you. Yeah, that would be you know it would be not complete. So we had to be more careful. Okay, so we have one example of a connected subset of R. Uh, is there a subset of R which is not connected? Well, of course, right? For example, the set of integers as a subset of R is not connected. Okay, why? Well, you see, let A to be minus infinity and let's say 0, and B to be minus zero point 0.5 and infinity. Okay, then so I have this. Here is 0. A is this part, and here is minus 1, and B is this part. So here I have minus 1 over 2, and B is this part. Okay, so you see A intersection Z is of course not empty. A intersection, no, B intersection Z is not empty. Uh, Clearly Z lies inside A and B, and intersection of A, B, and Z, right? Intersection of A and B is the interval minus 1 over 2, 0, the open interval minus 1 over 2, 0, and that interval contains no integer, right? And this is 0. So all these three conditions of being separation are satisfied. Hence, Z is disconnected. Okay. Well, to see more examples of both connected and disconnected subsets, we have to have some general results. One of them is the following. Okay, so proposition. All right. Let f x to y be a continuous function, be a continuous map, and E a connected subset. Then f of E as a subset of y is connected. So continuous images of connected subsets are connected. Let's see why is that. Let's take a separation for f of E. Assume on the contrary that uh, f of E is not connected. Say A, B are subsets of Y, open subsets are open subsets with the following. So f of E, first one, intersection A is not empty. F of E intersection B is not empty. F of E, of course, lie inside A and B. And f of E intersection A intersection B is empty. Well, we know that continuous maps taking preimage carries open sets to open sets, and this is what we will going to do. Let A prime be inverse image of A and B prime inverse image of B, which are both open, subsets of X because F is continuous. But then we have what? Note that uh, since taking preimage uh, preimage via F, we get, you see, let's look at this. F of E intersection A is not empty, but if I take preimage, I would get, when I take preimage of this, this is a non-empty subset of the image of F, right? Therefore, its preimage cannot be empty, right? And what is this? This preimage contains, okay, preimage of this is just E intersection F inverse of E, right? Yeah, I should say this. Preimage of this okay, this preimage is not empty and it lies inside E intersection F inverse of A, which is E intersection A prime. So E intersection A prime cannot be empty because it contains this non-empty subset. Okay. Similarly, of course, similarly, uh, E intersection B prime cannot be empty. We just repeat the same thing. And then what? E was, f of E is in A union B. So if I take preimage, f of E lies inside A intersection, no, A union B would give us E is in preimage of A union B, but this is equal to preimage of A and preimage of B, so that E would be in A prime, B prime. And the third condition, that f of E intersection A intersection B is empty, would give us what? This is empty, therefore the preimage of this, well, E intersection A prime, this would be empty, right? Because if there's a point here, if there's a point here, the image of that point would be in f of E. The image of that point would be in A and would be in B. Therefore, this intersection would be non-empty. Therefore, this is empty. So this means A intersection A prime B prime is empty. Now I have what? Uh, okay, we have the following. Let me now summarize. I have two open subsets, both open subsets of X, and they satisfy this condition and this condition together with this condition and this condition. All these conditions tells us that E is disconnected. Hence, E is a disconnected subset of XD. Okay. Of course, this is the contradiction, which is a contradiction. Why did we ended up with this contradiction? We ended up with this contradiction because we assume that the image of E is disconnected. Therefore, hence, uh, thus f of E must be connected. Okay. So image of a connected set must be connected. All right. Uh, do you have any questions? Okay. Okay, I said this interval is connected, but I didn't say anything about the other intervals. All right. Yeah, I still have to do some work. Uh, okay. All right. Another simple result is the following. Uh, assume that uh, E alpha in some index set. Uh, okay, maybe I should try. Assume that is a collection of connected subsets of a metric space, so that this intersection is not empty. So I have bunch of uh, connected subsets and they have a common point. Okay, then their union is connected. Okay. By the way, I already passed time. So let me stop here. In the second hour, I'll prove this theorem.